Thank you and welcome everyone. My name is Gareth Lloyd. I'm General Manager Corporate Affairs for the Global CCS Institute. Welcome to this webinar from the Institute. It's one of a series that we run featuring experts across the CCS chain. Today's webinar is CCS Major Project Development Lessons from the ZeroGen experience. In a moment, I'm going to run through some housekeeping matters, and then I will introduce our speakers and our panel. So our panel and speakers. So the main speaker is Professor Andrew Garnett, who's Director of the Centre for Coal Seam Gas at the University of Queensland. So he's newly appointed to that role at the University of Queensland CCS program, which is part of the UQ Energy Initiative. And he's also Director of the UQ Centre for Coal Seam Gas. He's a former Shell and Schlumberger executive. He's over 25 years worldwide experience with oil majors in conventional and unconventional hydrocarbon exploration. Prior to joining UQ, Andrew consulted widely on unconventional and acid gas developments, most notably those with high GHG emission footprints. And of course, he worked on the ZeroGen IGCC and CCS project as manager and ultimately as CEO and project director. So Andrew will be doing our presentation today. And on our panel with Andrew will be Martin Oettinger, who's Deputy Director of the Low Emissions Technology Centre, ACALET. He's Deputy Director of that, which is part of the Coal 21 Fund here in Australia. It's aimed at facilitating early demonstration of low emissions black coal technologies. Prior to this, Martin was with the Global CCS Institute as Principal Manager Carbon Capture. His 30 years experience plus in senior technical leadership and management roles with Australian and international blue chip corporations in power, minerals and hydrocarbon processing. The last 15 years of Martin's career have involved large-scale first-of-kind developments, including, importantly, 6 years in a senior technical leadership role with ZeroGen. So I can assure you we've got the two best people to present on this project, and I'll hand over to them in a moment. What I will do now is just explain one or two things about how the webinar works for those of you that have not done this before. It's quite simple. We encourage you to ask questions, and usually our questions and answer sessions are really effective. Don't worry about waiting to the end of the presentation. You can actually put the questions in the little box that is on your screen, write the question in, and we will do, and I will do my best as MC to present those in the time we've got available. So you can do those questions as we go, and also, of course, if anything occurs to you in the answers our panel gives. All very simple, but an interesting session going. So we will also wrap up a minute or two before 6 o'clock, but it's my pleasure now to hand to Professor Andrew Garnett, who's going to lead the presentation.
Okay, so I think I'm on now. Good afternoon, ladies and gentlemen. I'm going to go through a few slides on our lessons from ZeroGen. There's a whole lot of acknowledgements and thanks to this. I'll save them mostly to the end. But first I'm going to go through 2 or 3 slides to give some context, because like many of these CCS projects, it had quite a history which shaped the ultimate story. It's important to understand that context in terms of some of the lessons. And then rather than going into any of the real technical nuts and bolts of what we were going to build and weren't going to build and what we did and didn't do, I'll nip straight into the lessons and hopefully have us wrapping up in about half an hour or so. So just moving into this in context, these first few slides, it was set up as a small project company called ZeroGen Pty Ltd, owned by the state government, so funded in, if you like, in an equity sense by the Queensland state government, and sponsored or funded in a grant sense by the federal government and by the Australian Coal Association through its Low Emissions Technology Fund. And there in blue is really what it was trying to do, facilitate the development of commercial accelerated low deployment coal and so on, with a view to the competitive use in the future of Australian black coal. it's quite interesting to see that written down as facilitating the development of, because if you think of that as an objective statement, already you think, when I get to that, how do I know I've facilitated that development? So it's not quite a smart objective. However, it sort of says what it does on the tin, although it's somewhat difficult to measure. We were going to build an IGCC plant with CCS. It was around about 500 megawatts, 400 megawatts net. And we had two capture and storage objectives. The first one, which was a minimum requirement, was a 2 million tons per annum objective. And the second was a 90% or 3 million tons per annum objective. And what we had to design was something that would do the first one, do 2 million tons, but could be scaled up if the future required it to a 90% objective. In terms of where we are in the world, I'm sitting down here in Brisbane right now, looking out the window into the beautiful evening sky. Where we were is up where that yellow star was both where the plant was going to be and also very close to the source of the coal for the plant. The green boxes there were greenhouse gas storage tenements, about 40 or so kilometers from the plant, just south of the town of Emerald. The little red dots within that green are actually gas fields, pre-existing gas fields. I'll just point out while I'm on this slide, they were the only greenhouse gas tenements available in Australia at the time this project was done. I will mention later on in the presentation an area here called the Surat Basin, a few hundred kilometers to the southeast, which turned out to be another area we would have had to look at and go and explore, as the first area did not prove suitable, which effectively meant a design change from 40 kilometers from the plant to over 500 kilometers from the plant, or would have done. You see, it's a fairly remote location. It's 370 kilometers from the nearest port, which is Gladstone, and it's 800 kilometers from the biggest port, which is down at Brisbane. There's not a lot of very large infrastructure there, not a lot of large cities and so on. Brisbane's a population of 2 million, but nothing else in Queensland comes close to that. So it's a fairly remote site. Moving on, I'm going to go through a little bit of the history, going all the way back to 2006 when the project started off actually as part of a power company called Stanwell. It was later spun off into a special purpose vehicle. And it started off as quite a minor project, an 80 megawatt IGCC plant with a small pipeline into this area. I've just done the green area on the previous map. A couple of wells to be drilled to confirm that a little bit of injection could be done, and with hopefully then just a very limited demo size. Those wells were drilled but were not very promising, which then of course, willing to go on, shrunk the project down to a much smaller storage, but still an potentially interesting demo, sub-commercial scale obviously, with perhaps a trucking solution. And that required drilling some more wells. Now, in the time that scope change had changed, and the time required to plan the additional storage work, scope changed again to a 120 megawatt plant, slightly different technology. I'll go through the selections in a moment. And again, it was realized that the previous exploration program wouldn't sort out sufficient confidence for the 120 megawatt plant, so another storage exploration workup program 2B was designed, and as that was being planned, scope changed again. So the scope changed up to a 60 million ton, the final scope if you like, as it was decided at the sponsor level that it was really time to discover whether a really large scale plant could be done, that the learnings from a simple demo plant probably wouldn't be sufficient to give certainty about CCS in onshore Australia, or at least Eastern Australia. So obviously a major scope change. All through this time, however, the amount of territory available for storage didn't change. It was all the same right up to the end of the process in 2010, when in a different area, as we were coming towards the end of our pre-feasibility study, a different area, they created some tenements, and the government actually created a Greenhouse Gas Storage Act. So all the way through the process of the 60 million ton large-scale plant, we were running away in this rather limited area and chasing various funding options and so on. Throughout that process, we investigated 6 or so different gasified technologies and options, and different capture technologies and so on. That's just a list of them there. But you can see the sort of engineering input that goes on every time you change the scope. Go back to square one. we ended up with Mitsubishi being the prime provider at the very end. And if you need more details on that, Martin was there during that process. So again, this is what we were looking at. Simple coal handling and drying. And in red here, there are various different locations that you have to balance when you're trying to build one of these things in real scale, not at demo scale. So of course you have to consider where the mine is, where you're going to get coal from, how you're going to get it from A to B, large quantities. You have to consider where the slag and waste is going to end up. You move through to sour shift. There's a significant water treatment and raw water requirement. We're in a quite an arid environment here, so the location of water became a major issue. Up here, where we of course have to tie into new transmission lines since we're not in a very heavily populated area, and then ultimately somewhere to stick the stuff when you've pulled it out of the ground. Now, interestingly enough, you have to know where you stick the stuff in order to understand composition and pressure limits that feed back into at least into the acid gas removal. So in some ways you can do as much engineering on the left-hand side of this diagram as you like, but you can't complete any of the engineering until you understand location E, and you can't do any economic balancing really in terms of the economic optimum location until you really figured out you've got a location E. So there's a whole load of issues out there. We were somewhat constrained on our storage locations through licensing reasons, and also somewhat invested in it because of previous work done, even though that wasn't all that promising. So I'll go straight on to the lessons. Lesson number one is not really a new lesson. This is a graph from 1981. So it's about cost estimate growth. It won't surprise you in the major project world. This graph is an old-fashioned type of estimation class. In any case, the story is the same. Number one here on the left hand is the final cost, and the first dot just shows the cost growth. If I just recast that graph a little bit, so that one is now the initial estimate of the R&D phase, that sort of shows cost growth through the project. It goes up to about 2.5 times an early R&D estimate. And then I move on to these. The squares there are ZeroGen's estimates. We closed the project here at 6.9 billion. And the red ones are published figures from the Duke Edwards Port numbers, which grew. So I don't have the original red triangle equivalent for the R&D estimate for Duke Edwards Port, but the cost growth is fairly similar. It's what should be expected in major projects, certainly in major pioneer projects, which was that original 1981. So lesson learned, cost growth was significant, or we shouldn't have been surprised at that, and no one should be in this CCS world. Again, from the same era and the same type of study, despite what you read in most of the comments about CCS, the cost growth does not come from regulatory standards and does not come from other unforeseens. It comes from the quality of your engineering in the first place. So your cost growth comes from the quality of your engineering, the percentage of your capital cost, which is new technology, the complexity of the plant, the degree of project definition, that's directly the number of man hours, and the degree of process definition. And for us, integrating very large scale IGCC with CCS, it's not so much that the processes were immature, it's more that the integration was immature, and for the degree of process definition should raise a big red flag about cost growth through the process. So not new, but learned. And here's the numbers we had from the pre-feasibility study phase. We closed at the end of the pre-feasibility study phase. And perhaps the thing to notice here that the vast majority of the costs to the end of pre-fees are CO2 storage costs. These are all costs at risks, and in this particular case, the costs went ahead and showed that there was no usable storage in the tenements available. I think maybe the other thing to look at there is, while we all focus on plant and capture costs, really at pre-fees running into feed, costs at risk are predominantly on the storage side of things. We then did a significant amount of effort, several hundred odd thousand man hours into capital cost estimates to close, so cost to go, CTG there. And again, to look out here, this is the benefit of doing commercial scale work in a real location for a real plant with real contracting and real logistics constraints. So you see there, of course, power plant is a large amount, but this enabling works is costs that you would not know about unless you did it in that location. Bridges and roads and water and various other bits of infrastructure, which are very location specific and not at all obvious until you have a real physical location to deal about. So there's a real benefit in looking at real large-scale commercial work in terms of understanding cost structures, because a significant amount of cost structure are very location-specific. The other thing to notice here for this cost to go is we have a 800 million figure for carbon transport and storage. That's only a scoping level cost estimate. This is actually looking for an entirely new area. We'd already written off one area. So there's a lot of scope for that particular number to both grow and shrink, you would say, hopefully, but probably to grow. And it's a different class of estimate to all the other estimates on the table. The cost growth from our 2008 scoping study, a 4.3 billion study, we came up to 2009 to fix for exchange rate escalation, and then we had cost growth, which is basically because we did a lot of more engineering work. So you can see the major thing, which is design work, but not forgetting some of the major other issues. Infrastructure scope increased, and of course escalation factors to 2016, and we were supposed to have built the thing. And if you're in a political process where it gets longer, that escalation box of course goes up every time you waste or lose 6 months around an election. So the escalation factors in a project which have significant political stakeholders have to be managed pretty carefully in terms of your forward cost estimate, because an optimism on the time frame is effectively just the same as looking for a massive growth on escalation as you slip. In 2010, after we'd done all this work, the ZeroGen management, that's myself, Martin, and Chris Gregg and others, we advised pretty clearly that this should not go ahead. It's a very high capital and operating cost. It could not be supported by the revenue streams. There were remaining technical risks, not so much about the capture technology, more about the actual integration with a capital I. We could not find a way credibly to fund the project going forward to a financial close. We did not have in the available licenses at times somewhere where we could put the storage resource, and even if we could, it would have been well over $100 a ton, even if the area was the same reservoir but had been bigger. And we simply didn't know when there would be another tenure coming forward where we could start looking for other storage resources. So we didn't want to embark on a feasibility study, which would be $400 odd million, without understanding whether in any time in the future we'd have that storage resource. What we did manage to do, though, and all of the funders were excellent in this, was recognizing that we'd gone through all this work and effort. There was an opportunity here to capture some lessons, and effectively that's what you're seeing now. Lessons coming in seven buckets, something about the market scale and the economics, something about risk, something about the nature of the goals, particularly around storage, and the normal stuff about front-end loading. I won't dwell on this slide, I'll go through them one at a time. So the real lesson is, and particularly if you put this in context of 2010, that it's really currently not, certainly in a Queensland and Australian context, the very large-scale CCS with IGCC are simply not economic. You cannot close them. And furthermore, the cost structure for a well-engineered project are significantly above almost all published costs you can find. That's a typical cost growth lesson relearned, as I mentioned earlier. Couldn't close the gap. We were well above the upper limit. We could not find a way to build one of these things and make it financially viable in the way the current electricity market works in Eastern Australia. I can go for more on that in questions. There are some specific things that it needed, but effectively it needed significant capital subsidy, significant ongoing operating subsidy, and a special place in the market, a must-take requirement in the market, which was no way to get that in the time available. The situation was also exacerbated in an Australian setting. At that time, there were several major projects, both in the mining and the gas industry, which were basically sucking out labor and driving up all costs, labor and capital costs at the same time. So some of this is Australian-based, particularly the high costs and relatively low productivities, but generally otherwise, if you're going to build one of these things, you need a special place in the market, at least for a few years while you're running it. The other lesson is obvious, but worth stating. You learn a lot from industrial scale in a real location that you can't learn otherwise. So in other words, in fully to understand how a CCS power project will run, you need to really engineer it at scale. That sort of scale brings the reality checks to you. It brings the real questions. Do I have to expand the port? Do I have to build a bridge? The sort of normal things for major projects which you don't get in a desktop study very often, and particularly ones which are specific to balancing those 6 locations I mentioned on an earlier slide. So we also recognize that what you really need to do way up front before you start spending money on significant engineering hours is be significantly more confident that you actually have a storage resource. Those are funds that someone has to put at risk. Obviously in the traditional oil and gas sector, somebody puts those at risk. It's typically an equity company who works out some benefit from that. But putting funds at risk in an exploration program is very difficult to do in this space. There's no it's very difficult to get a funding body to do that. The other thing about such a program, of course, is that if you have a bunch of potential storage sites, you need to have enough of them so that when you drill them up, there's a good chance that at least one of them will pass. And that chance of passing and that tolerance for risk, or that tolerance for writing off exploration costs, has got to be well in line with the risk tolerance of your funders. So the next one is really about PES. So we had 2 things going on during the project, and it's first, the second bullet point there is we thought in hindsight extremely important that the first one of these carries the burden of proof for all the other ones. In other words, it requires a very conservative approach to risk management for the first very large scale one of these. In other words, you need to be very conservative and very measured, particularly with your environmental impact assessments and your public consultation process. However, that's run somewhat counter to the push that was going on around 2009-10 to get certain operational start dates very early, and in some cases to spend available funders' budget within a certain calendar year. So you have an inherent tension there in that you actually need to be very measured and conservative, and yet people need to see successes coming forward and need to get money spent at a certain rate. What we saw, and what I think I'll show in a moment, is there's a way to risk optimize schedules, and there's a way to not do it. So you can parallel, as we did, you can parallel storage exploration and appraisal with engineering, or you can be a bit smarter than that. And before you start putting significant engineering dollars in, you need to have sufficient confidence, and that's a conversation you need to have with your stakeholders. What is sufficient confidence that it's present and that it will perform? And in order to do that, and it's licensable, of course, in order to do that, you need to drill some wells and you need to test that stuff. So this is your risk optimized project. You actually have a bunch of work pre-project, which may involve some engineering. That's the bottom of the 2 left-hand boxes, some scoping and potentially pre-fees work. But at very least, you have to get some drilling done and some testing done before you significantly invest in engineering. In some cases, you might not do even pre-feasibility until you've done the appraisal of the sites and done some significant dynamic testing. The next one, of course, is a typical question we always learn from pioneer process projects, that pre-feed, this is in the oil and gas sector, your pre-feed costs and risks are all about storage, and particularly our at-risk expenditure. For us, it was 70%. It could well have gone up to 90% to end pre-fees had we gone to another area. It's particularly important to notice here that it seems to us that people getting far too much confidence from Atlas-type estimates that have been published in various studies. They don't really give you any confidence that there's an appropriate rate-match storage available. The only thing that can do that is if you're in a play where you have significant dynamic data already and that's been incorporated into models. And I'm just going to show you an example of what happened to our storage works. So this is the question, are there any storage resources that can perform as required, and are they developable? Developable is 2 estimates. One, of course, is cost and technology, and the other is public and environmental. So on that table at the bottom, on the left-hand side, there are 2 lots of estimates. Aldebaran, Freitag, and Catherine, they're different geological formations, and we have 2 different types of estimate. One is a Queensland storage atlas. It's one of these atlases we mentioned, and it assigned a certain range of tonnage in terms of capacity. And then there's the ones we did with a similar but different methodology, and we got effectively static numbers, as they would be called, which are not that different. And then we actually got the engineered results, so if you like, the results which come after drilling wells and testing. So what we found was, first of all, these Aldebaran, Friedegg and Catherine simply is not an injectable formation without significant fracking, and in this case in particular the fracking probably wouldn't access the formation. So effectively that 180 to 100 million tons doesn't exist from a practical point of view. We then found that if we didn't have any license constraints, we could indeed put 54 million tons in the Catherine, but it would take 120 years to fill it. We then found that if you had to just limit that by the field development plan, so what you can actually build in time and the 10-year time frame, you might be able to get in 25 million tons, but it would cost you over $140 a ton. So effectively the practical capacity which goes with these Atlas estimates is zero. It has no relationship to those estimates, and you can't come up with a practical capacity until you've done some notional field development planning and some dynamic tests. So the real lesson here, I guess, for me, and it may be contentious, is that the Atlas estimates don't help. So it's a natural resource. If you don't know where it is and it's not well drilled up and well tested, you're going to have to allow for a portfolio exploration program, including significant failures, and you're going to have to figure out how much you've got for that, how much money you've got for that, and what tolerance you've got for that. And furthermore, you have to use the mentality that oil explorers use, which is far cheaper to seek to kill an area or a play than it is to seek to prove that it's there. So you find the killer data and your first well targets that, and if you find it, then you don't end up drilling a dozen, you end up with one. The other one, which is a classical exploration problem, particularly when you get those things which are marginal, is you have to know and define before you start going in that area to define when to stop. And when to stop is about, given the data available, the confidence levels you have in getting your target. For us, our target was a total of 2 million tons minimum, per annum minimum, at a cost of $50 a ton. So once we'd done enough experimentation and enough drilling and testing, we could say we had absolutely zero chance, or a very small chance, of getting anything like 2 million tons per annum for 30 years, and certainly no chance of getting it at $50 a ton, even with imaginary new technologies. But that pre-definition was the key point. The other thing we found very clearly was there's quite a difference in engineering, whether you're engineering for rate or engineering for cumulative volume. So what we saw was a lot of targets in terms of gross volume. You have to put away 60 million tons. Now that's a very different engineering problem than doing 2 million tons a year for 30 years. So what needs to be done very quickly is to recognize that these are all rate limited problems, go away from these volume targets and particularly define storage targets in terms of rates, sustainable rates. Sustainable rates then drives you away from atlases and drive you towards proper dynamic models. The other thing we found, which I think was a very useful thing, is that you don't need to test with CO2, at least not initially and not for purely technical reasons. In fact, testing with CO2 gives you poorer data than testing with water production or injection with water, because your key uncertainty is reservoir connectivity. And CO2 being compressive is not a great fluid to check for that. And a lot of the reactive issues that people are worried about, do them in the lab first. We needed extended well tests, and everybody's going to need extended well tests, most likely water pump-off tests, possibly injection tests. You also need, at the very early stage, what you'd call in the oil sector a conceptual or notional field development plan, so that you can constrain it by real features. We had areas of natural scientific interest. We had areas which you couldn't drill because it was too close to rivers or too close to people. And so you have to start constraining your features, because ultimately there is a physical limit to what you can put on the ground, and you need to get to that with a real plan, with a real field architecture. And then finally, given that when you're injecting, you've got a constant rate coming at you from the plant, when you're injecting you have an increasing reservoir pressure, you actually need to continually drill in certain areas to manage that pressure increase, so that you don't have to vent the gas coming at you. So you need to simulate drilling sequences and figure out how that cash flow moves over time, and whether you can actually whether you can actually do this, whether you can actually maintain the rate, or whether you have to venting or have some other different alternative site or redundant wells. And finally, which is not surprising, very high front-end loading. It's because the integration is not mature, and it's especially not mature at the location, which won't be mature for 1 weeks. So it's not just a matter of integrating well understood proven technologies. We've heard some statements, or we did back in 2009-10, and we felt strongly that that sets an unreasonable stakeholder expectation. Yes, the technologies are mature, but the integration is not. We also have to get that extra engineering because before you go to FID for this, you need an electricity market context, and you need significant engineering to give yourself some confidence so you know how reliable this plant is going to be and what sort of power offtake agreements you're going to need. And you don't really get a feel for that until you've done significantly more engineering than would be normal for a conventional plant. You also need it for financing, and you also need a final point there is when you've got all this front-end loading and you've maintained a team, you need to have a funding arrangement which allows you to sustain that team through the various project reviews and inevitable delays as things move either between phases or you have changes of funding personnel or changes of government. And in fact, that was turned out, in hindsight, one of our major problems was simply holding a team together while we had these hiatuses. So and then I'm coming to an end, but I am at an end. I'm ready to hand over. I'd like to thank everybody who ever worked with ZeroGen. Thank you all those who worked with us, the former Queensland government, Australian governments, and the Australian Coast Association. And I think I'll hand over back now to Gareth.
Okay. Thank you very much, Alf. That was instructive. And just before I forget to mention it, I would say that there's an absolute goldmine of information in the report that Alf produced after ZeroGen. That's on the University of Queensland website, which we'll show at the end of this webinar. And I certainly commend that to you. I've been through it from cover to cover, and there's a wealth of information there, and certainly worth looking for that on the UQ website. So in terms of taking CCS forward, Alf, if we're really going to accelerate CCS, once we've learned from these kind of first generation plants, what do you see coming out of that? You've made a lot of points about storage characterization. In terms of the pathfinders and the learning, if we look forward for the next 7 to 10 years.
Yeah, my fear at the moment is, and cards on the table. I come, as you probably guessed, from an oil and gas background. But so cards on the table now. There simply is insufficient real evidence that the amount of storage we need in terms of rate, so matched rate, there's insufficient evidence that that's available to us for the CCS mitigation wedge. And if you marry that with the amount of exploration activity for CCS, which isn't happening at the moment, if nothing happens in the next 10 years to effectively increase the rig count looking for sites to put CO2 in, we're simply not going to get there. We simply don't have the supply chain which can deliver that wedge. And the critical path for us, and certainly onshore Australia, and I suspect predominantly globally, is that until those sites are actually verified rather than just a desktop study, we're in somewhat of a dodgy position.
And so, I mean, you refer to the fact that you actually located another storage location that was about 500 kilometres away. Is that right?
Yeah.
So, and the atlases that you used for the desktop study were really not, what if anything, misleading. You know, what would be your message to those that are involved in projects or potential projects at the moment?
Well, they're not misleading. They're not generally misleading for someone who has a sort of typical industry background. They are somewhat misleading, I think, to some of the high-level decision makers. You see 100 million tons, and you know you have 10 million tons a year to get up to get away, and so you then do one divided by the other, and you think you've got 10 years of storage. So they're not inherently misleading to those if you like, with experience, but they can be very misleading. Where they are useful is particularly on what the exploration people would call a play analysis. So those people which identify the presence, for instance, of regional seals and potential reservoir units. So from that perspective, they're useful. But really what you need to get down to is the dynamic behavior of those. And the only way to do that, if you don't have an oil and gas field nearby, the only way to do that is essentially to drill some wells and test it.
Yep. One of the things you actually made a strong point about was that some of the time constraints that you're operating under were quite aggressive. So you were running the project in the way that you want. If you hadn't had some of those aggressive time scale pressures, how could the project of the ZeroGen project have proceeded differently? Because I think that was a strong point that ran through the presentation.
Yeah, so notwithstanding that, you know, ultimately that you have to get to financial close on these things, but if we park that for a moment, there would have been a pause, effectively a pause on the engineering while that additional area was explored with a little bit extra seismic and some drilling, which is probably a 3 to 4 year program, or a 2 to 4 year program. If you're lucky, it's 2, and if you're not, it's 4. Till you get a very high level of confidence that it's indeed worth doing any more significant engineering. So there would have been a few sort of studies on the side, you know, some likely area studies and some transmission studies and so on, some pipeline corridor studies, but not significant engineering until really you can look your investor in the eye and say, yes, I've got a better than 60% chance that I can get 2 million tons a year for 30 years this place. So 2 to 4 years of additional space. And then it would really depend on the quality of what you found. It could easily be another 2 or 3 years, or it could be a very quick EIS process, another year or so.
So are you suggesting if you'd had those additional timescales, that the project would have turned out differently?
No, I think we would still have been. It didn't have a I think it didn't have a single, a single killer issue. We would still struggle with the cost base and with financial close. Placing operating subsidy, capital subsidy, price in the market, and very high cost. And if you put into context a $7 billion-ish project, which would effectively have given 400 net megawatt plant with a similar sort of emissions profile as a CCGT plant, which we could bring in at around 3. So it started to make not only not much sense from a financing point of view, from a financial closure point of view, but even then, you've got to question, is that the best way to spend that much money to bring CO2 emissions down?
Sure.
Remember, Australia is and was a particularly high-cost environment.
Yes, and you touched on that through the presentation. But just in terms of taking it on, and actually to encourage our listeners that are on the webinar, please do put your questions in here, because this is your opportunity to ask questions when you read the report, which I was saying is excellent. There may be lots of questions that come up, but here's another one from me. Would there have been, looking back on it, because we were talking about lessons learned, is the value in doing something at a, say, 150 to 250 megawatt scale in Queensland or Australia to actually progress things? So, i.e., quite a significantly smaller project.
We're also no. So I think the short answer is no, but it's rather a long answer. First of all, as you know, we're in a declining energy demand. We're in a declining electricity demand situation here at the moment. So putting anything extra in the market doesn't make much sense at the moment. So notwithstanding all the other technical issues, no. The unit cost wouldn't have been particularly any better, and you'd still end up with Australia's whatever you build is going to be expensive. So if you're intending to build 150 megawatts to learn something specific on the process, and we thought the process required scale, so in other words, you wouldn't learn at 150 what you would at 500, and particularly with all those locational and enabling contexts. So the answer would effectively be not really. But I'm happy for Martin to jump on that one because he loves engineering.
I guess one of the lessons out of the ZeroGen project from a power generation technology perspective, it highlighted, I guess, some of the things in relation to IGCC, is that it was an all or nothing technology in regard to carbon capture. That and as Alf has already pointed out, the IGCC at less than fully commercial scale, some of those lessons wouldn't have been borne out by doing something at smaller scale. In regard to IGCC, just for power generation in Australia, very, very tough, very high cost. You would have been needing some other product out of it, such as what you're seeing happening in the world in other places. Things like the production of fertiliser and chemicals and fuels that might have seen a better value proposition. But IGCC just on its own for power would have been a difficult ask and would still be a difficult ask.
Yep. And just another one for you, Martin. Any other lessons learned that sort of stood out for you specifically in terms in particular of the engineering and integration? Because Alf touched on that. Probably a question for both of you, but I'll start with Martin.
I guess one of the things that was really evident was the deployment of carbon capture technology in hot and arid contexts. What you're seeing, certainly in a lot of the places in the world where CCS is going to be deployed, they are very hot and very arid contexts. So there needs to be a lot of attention placed on the utilisation of water and the utilisation of appropriate forms of cooling. One of the forms of cost that actually came in the project was when you started to have to deploy technology, in this case pre-combustion capture and IGCC, in that hot and arid context. That added substantial cost. I should say MHI did a fabulous job on the in regard to their component, the engineering on the IGCC, as did UOP in regard to the carbon capture. But when you actually brought those two technologies together, and you then needed to look at the need for dry cooling and the need for minimising water usage, and particularly the deployment of zero liquid discharge, that added substantial cost to the the capital cost of the project, as well as operating cost, and that's something that's going to be faced certainly in China, in the United States, parts of Europe, even Australia as well.
I think I'm right in saying, just as a sort of an addition to that, Martin, this was a period when Australia was going through a pretty serious drought, so that presumably made it just even tougher.
From a stakeholder perspective, yes, you started seeing once in 100-year droughts coming in, which certainly exercised the minds of some of the regulators and those who would be granting license for the project, and that sort of put added pressure on let's say on the project to come out with acceptable outcomes.
And a question for both of you, which is on the broader material that's in the report. Any particular lessons learned in terms of managing the stakeholder relationships? I mean, I know that the project, as you pointed out, Andrew, was in a fairly remote area, but nevertheless there'll be some stakeholder issues. I don't know if you want to give any comments on that.
Not sure. So a little bit goes back to the management of pace as well, but certainly the management of local stakeholders, as is not surprising to anybody listening, I'm sure, requires a lot of careful consideration and a lot of front-end consultation and engagement. In fact, we had a little bit of a surprise when we ended up closing down, in that if you think about it, we were engaging people around what is effectively a pre-feasibility study. And those with a major project background will recognize that the vast majority of pre-feasibility studies don't go on to make projects. So we actually, when we closed, we had some comments from communities in the area to the effect of, where are those jobs you talked about? So one of the lessons, certainly from my perspective, is although early engagement is generally agreed to be a requirement, it's got to be extremely careful that it's not seen to be overhyping the fact that there's in some areas an economic opportunity coming your way. And whereas we were much more focused on, the public concerns about the injection of CO2 and this new technology, we should equally well have been concerned about raising hopes in areas like this for jobs and future prosperity, which took us a little by surprise in hindsight, but it's something to be really aware of, because as I said before, the vast majority of these projects probably won't go ahead.
Yeah, so you've got to sort of manage expectations, and that is quite difficult in the complexity of what you're doing.
And I think that the community's focus in public engagement has been to reassure people that the technology is safe, which is fine. It's just not enough.
Yeah. No, that's bound to be the focus. And you talked quite a lot. Sorry, carry on.
Sorry, I was just sorry, Gareth. I was just going to add something. One thing with ZeroGen, it started its activities in around 2005. Since then, there's been, I guess, significant developments in storage type activities from a stakeholder engagement perspective, plus other forms of resource projects, certainly in that part of Queensland. The project actually, I certainly believe in the early days, did a very good job of making sure to, let's say, to be very measured in its contact with with stakeholders, and to develop trust. I think what's happened since then is there's been some excellent tools that have been developed in regard to public engagement, many of which are on the Institute's website. Certainly, if ZeroGen would have to be deployed now, or you would be contemplating something like a ZeroGen now, I think you would have needed, let's say, significant application of good good quality tools and a very much more measured approach. The world's moved on to a certain extent.
Okay, look, I've got a number of further good questions here. You mentioned the technical risk to CO2 capture technology. Which one is the most risky one? Our questioner asks. For CO2 storage, why EOR is not considered?
Oh, okay. No, that's a good question. So I'll, was that two questions there? One about the risk capture and
yeah.
So I'll take the storage one, and I'll pass over the capture integration one to Martin. The storage one about why EOR wasn't considered is simply because there are no oil fields within several hundred kilometres of this place, and the oil fields that are there, that we do have in that part of Queensland, are actually very small. So the requirement for CO2 is nothing like 2 million tonnes per annum. If EOR were to be suitable several hundred kilometres away, it's just not the opportunity for it. It's too small. The biggest risk and uncertainty on the storage side, once we've established that there's a seal there, and there are actually some gas fields in this area, so we're fairly sure the seal works. The biggest risk is reservoir continuity and the ability to sustain injection rate without raising the reservoir pressure too much. So it's reservoir connectivity and continuity was the biggest uncertainty, which requires well testing. Martin, you want to go on the capture integration risk?
I guess in regard to the capture integration, what you saw in the case of the ZeroGen IGCC with CCS is that application of a physical solvent process with an air-blown gasification technology, that was a first. That combined with the need for dry cooling, and also the other thing in regard to achieving certain specifications for the CO2 product, which may have been slightly different from what you may have seen if you were using it, say, in a chemicals application.
Okay. Look, there's one here from France. We totally agree regarding the need for a portfolio approach to regarding storage. Our estimate for real commercial scale storage is that 10 years seems reasonable for exploration, characterization, and testing on such a portfolio. What's the time estimate according to your experience?
It's very place specific. So it's a really good point to talk about. It's a really good discussion point. So how long will it take to mature my storage resource? And it's very dependent on where you sit in the world. So my expectation would be, if I were running around the northern North Sea, it wouldn't take that long. Partly because I don't have very lengthy land access issues where I have, in some areas here we have 2 hours to 2 years just to negotiate access for seismic and wells, for instance. So offshore in proven hydrocarbon provinces with lots of 3D data would be considerably quicker, and I would suggest in somewhere like the northern North Sea you're down below 5 years. In onshore Australia, not least because of permitting and access issues, you're probably closer to 10. And I wouldn't be surprised, knowing onshore Europe, if you're in that sort of space in a realistic setting. Now, it could be within that space that you're lucky. So in other words, if your very first activities are very promising, that would tend to bring that down. So the question is, on what basis do you plan on exploring your portfolio? You can either plan on the basis of my first wells will be good, or you can plan on the basis my last wells will be good, or you can plan on the basis of somewhere in the middle. What I would normally do is do that in a sort of probabilistic sense and come up with an expectation curve of how long it will take. 10 years is certainly not out of kilter. It's not a surprising number.
Okay. Another question here. Can you elaborate on the relationship between the purity of the injected CO2 and project costs, complexity, and regulatory issues?
Martin, do you want to do the? I'll tell you what, Martin. I'll start with the driver for purity from sticking it in the hole, and then you go into and then you talk about the cost implications of the acid gas removal unit. So one of the things that drives the need for purity, so your specs, is one, of course, is regulatory, and we have in the Queensland Greenhouse Gas Storage Act, we have a thing called it's overwhelmingly or predominantly CO2. The critical element for us is that you don't deliberately add something else into it. So it comes out of your AGRU, it's predominantly CO2, and that's undefined. It's got to be tested by a specific environmental statement. But ultimately, it's not pure CO2. It doesn't have to be food grade. It has to come out of your unit. So you have somewhere to play with in terms of separation technologies that you could potentially not overspec your separation. So the real controlling factor is the reactivity of your formations. In other words, you can't put any contaminants in there that are going to scale up, close down your permeability system, or cause minerals to drop out of your formation fluids and thereby also clog up formation fluids. So it turns out to be an absolutely critical cost element to understand the reactivity of your formations and the sensitivity of your formations, so that you can take that back to the design of the acid gas removal unit. Martin, do you want to take it on from there?
Sure, that's a good point. Most of these acid gas removal processes, and we are talking specifically here about pre-combustion capture, and some of these things may not necessarily apply to things like post-combustion capture. But in the sense for pre-combustion capture, where these the CO2 ends up going on some of these processes, it doesn't end up being in a geological storage. So being able to target different purity specs for this type of an application was often very different for how this technology was then deployed. One of the issues too is in regard to some regulatory. When you undertake a pre-combustion capture from a syngas process, there's the issue of odour. You can't just vent this CO2 that you end up capturing from these acid gas processes. There are trace levels of odorous compounds such as H2S. So you need to put those through some form of incineration or odour mitigation process. Now that adds significant cost. In the case of a post-combustion capture type system, things like, let's say, venting of CO2 doesn't necessarily have the same implications from from a venting situation. You tend to be able to turn those processes off, whereas in an IGCC it's buried in the middle of the process, and you're forced into a situation where you then have to vent the CO2, and that has those implications. If you want to avoid odours, you need to do something about it.
I think I'll probably just add, there are always, I mentioned the sensitivity of the geological formations, and there are the well-known sulfur stress cracking and hydrogen problems, and if you've got mercury floating around, these things are well known in terms of your material choice issues for your pipeline and compressors and your wells. So that's not new stuff, and you can engineer around it. What you can't engineer around is the rocks. Martin mentioned an extremely important point there. When you're designing, you need to get clear very early on your venting and flaring policies, both at the plant and in the field, because if they're overly restrictive, you end up spending a lot of money avoiding venting and flaring. So, for instance, in the field, you might like to have a vent. If you're not allowed to have vent, for instance, when sections of the field or compressors close down, then the only way around that is redundancy, which of course adds to cost. So, very early on, the conversation with the regulator has to be around the non-routine venting and flaring. How do you manage interruptions? Because if you need to design them in, it's a major cost inflation.
Okay, well, look, there's a lot of lessons learned there. There's another one here. I'm trying to squeeze as many questions in as I can. So what was the basis of the $50 a tonne target price that you referred to?
That's a really good question. It may even be lost in the midst of time.
Well, we can only ask, but
it's like this. Towards the time when we were looking at setting a number, we were going into either an ETS or a carbon tax situation, which looked like it was going to be around I can't remember what the original number was, Martin. It was about $10 a tonne or $15 a tonne or some small number to start with, and was going to ramp up. So we were not designing for a very low. Oh, the $50 a tonne, by the way, was only the storage cost. It wasn't the full. So it was just the storage cost. Yeah. So we were looking for this number, which was considerably higher than what the original ETS or carbon price looked like it was going to be, and significantly higher than, because we knew the first one would take some doing. So basically, it's roughly three or four times what the original cost. I don't know if there was any more science to it than that. Martin, do you know?
No, I think it just was looking at, given it's first of a kind, given that you're looking at the essentially the transport and storage aspects, you had to set a mark somewhere, and that seemed like a reasonable mark for a first of a kind.
It was a very easy. It's a fantastic question though, because it does come to the nub of what you are designing to. So we had two criteria in that, when we had a test at the end of pre-feasibility study, and one of it, we need a 50% confidence limit that it would be $50 a tonne or less, and a 50% confidence limit that we could do 2 million tonnes per annum for 30 years. They were the tests that we pre-designed up front, and therefore, because we'd had those predefined tests, we knew what we were engineering towards the end of pre-feas, and we knew whether we were going to go to the next stage, the $400 or $500 million stage, and go into feasibility engineering. So it's worth that stakeholder conversation, getting what's your confidence limit or your risk tolerance, and what are these go no go? What sort of confidence levels do you need in the go no go series? And that's quite a tricky decision for many stakeholders.
Okay, excellent. So I'm just going to squeeze two last questions in. You've talked a lot about lessons learned. Was there a point earlier actually in the project where, with hindsight, it may have been better to have called a stop to the project?
There was a hindsight engineering is always a wonderful thing.
Wonderful thing, yes.
There was a time, whether it was a stop or not, I don't know, but there was a time when, if you remember, there was a big scope change. So basically, it was decided to go very large scale around the same time, and there was probably, whether that would have been a stop or not, but certainly a more in-depth pause and review at that stage, because effectively it's an entire frame change for the project. The other ones were messing around between 80 megawatts and 120, and then suddenly effectively was his entire project change. So possibly whether it would have been a pause or not, I don't know, but it certainly would be a red flag that says this project has just significantly changed, and time to stand back and take some time to do some more in-depth technical reviews, in-depth technical and commercial reviews.
Okay, and just kind of related to that, any lessons learned in terms of sort of managing all of this around regulators and governments' timescales?
That's also a fantastic point. I think the critical thing you have to understand, and this was a very specific project which had 2 governments involved, and you have to recognize very early on and get to learn very early on their own planning process and their own sensitivities, and you've got to really be very perceptive to their own risks and risk tolerances and sensitivities, some of which are nothing to do with the engineering, some of which even are to do with projects going on elsewhere in the state. So I think there's a real lesson here in the amount of in-tune radar you need in this sort of a project, and the amount of engagement you need and understanding you need of your political funders is quite exceptional. It's much more sensitive, and there are much more things coming out of left field than a simple arrangement between 2 commercial entities. Martin, do you want to add anything, or does that sound that sensible?
That sounds a pretty good overview. I guess the one thing as well is that it is a process of discovery as you go through, and it's being in a position to feed those elements back. There should also add that this project was conducted over the period 2005 to 2010, and there's been a lot of lessons learned since then, and that's those sorts of things weren't evident at the time.
Okay, look, just to cap it off, just one last question. How did you convince yourselves that the store seal was competent and had not leaked gas in the past if there were other gas-filled reservoirs nearby?
Oh, yeah, okay, that's a fairly good question, and wonderfully a very cut and dry one. There were some distance away up a structure. There are some existing producing fields, and when you drill down to those, first of all, when you drill down to those fields, there are no gas shoals above the seal. So in other words, in a geological time context, those things were not leaking. The seals were highly competent, and in fact retain a fairly high gas column. You can actually work out then a minimum entry pressure from the gas column that's been held for the last 20 million years or more. So you get quite clear that in that up-dip position, the seals are very competent, and you even have a measure of how competent to a minimum standard. The argument then goes, as you move down dip, and where we were was off flank and down into an aquifer in the base of a syncline actually. Those stresses that keep us, in addition to the stress to the pore throat entry pressures, which increase because you're going deeper, which you go deeper, all the stresses start to work for you. So that was the first thing. It's a straightforward physical argument to say if a seal works when it's shallow, it's even better when it's deep. And actually, it's even where it was deep, where we were looking, it's also a good deal less faulted. And then we measured it. We went in and measured it both in core samples in the lab, both with air, mercury, and CO2 injection pressures. But more importantly, we measured it in the wells, and we measured fracture gradients and leak-off tests and so on. And actually, we had a seal which was so tight, we actually couldn't find a way to make it leak in some of our tests in the lab. It was an extremely good seal. Unfortunately, the reservoir was quite a good seal too, so didn't work out how we wanted it to do. So I hope that's the question. The seal question, once you're in a hydrocarbon play, is actually a relatively easy one. The more tricky question is sustained injectivity.
Okay. Look, that's a good question to end on, and we are out of time, in fact slightly over out of time, but I have carried on because I think we've had some really good questions here. What I'd like to do is just sort of summarise by thanking our panel, but in particular, before I do that, just saying that if there are some outstanding questions, send them in to us, and we'd be pleased to give you answers to those. We'll be putting the recorded webinar and presentation slides on our public website, the Global CCS Institute website, in the coming days. The report itself is on the University of Queensland Energy website, and we'll leave you with the information on where to find that. So you should see that on the slide now. So take a note of that. You'll easily find it. So in thanking our presenters, Professor Andrew Garnett and Martin Oettinger, I'd just like to say that you've unlocked a wealth of learning there. So you mentioned the process of discovery, but there's a tremendous amount of learning there. Thank you very much on behalf of everybody that's been on this webinar for your time. It's as part of a series of expert webinars from the Global CCS Institute. We hope that our audience found it useful. We do value your feedback. We're always keen to make these as good as they possibly can be. So at the end of this webinar, there's 3 very quick questions, and we'd appreciate a moment or 2 from you to answer those so that we can improve the program for the future. So with that, I'd like to thank you for your time. Thank you everyone for joining us, and thank you again to our 2 presenters. Thank you.
Thank you.